So far, we've talked about surfaces that are made up of just one substance, but often we'll have a surface that's patterned, that has elements made up of one type of material and elements made of another. And so we imagine having a surface like this. We can imagine, for instance, a droplet being on a checkerboard. So in this nano checkerboard, imagine that we have a material that's the yellow squares, which has got one contact angle, and the white squares has a different contact angle. So what's the measured contact angle we're going to get for this drop? Well, we can calculate this with the Cassie-Baxter equation. In this equation, F1 and F2 are area fractions. And theta 1 and theta 2 are the microscopic contact angles for those areas. So this is a way of basically making a weighted average, weighted by the different areas, to give us the angle that we would observe. This equation does have to be used with caution. The area fractions that are relevant are only those that are in the perimeter zone at the edge of the droplet where the three faces come into contact. We imagine a situation as shown in this other diagram where we have this kind of bullseye type patterning. If we look at our droplet edge, it's all within the white phase. It's all within that white material. So the contact area, the contact angle that would be observed would be just that of the contact angle of the white material. The yellow material is totally irrelevant since it's not found in that contact line area. So we just make a little notation here that it's not applicable in this type of geometry. Let's do an example. Let's imagine that we have a surface that has pillars on it. So we imagine looking down on it. We look down at this surface, we see it has these little bumps. And our material is hydrophobic. We can see it's got a contact angle that's non-wetting. And so it's going to be hard for the liquid to go down and wet these little spaces between the bumps. And so the water droplet will just sit on top of these pillars. This is exactly what we saw when we looked at dew droplets sitting on top of leaves. We saw that there was air underneath the droplet. Okay, so let's figure out this problem. Notice it is different from the Wetzel type regime where we actually have water actually going into these, filling in these spots. Okay, it's actually sitting on the pillars and on a cushion of air. The cosine of theta observed is equal to F1 cosine of theta 1 plus F2 cosine of theta 2. We have to figure out what these things are. Well, the pillars occupy 30% of the surface. So let's say F1 is equal to 0.3. That's the fraction of the area taken up by the tips of those pillars. And the contact angle for the material where it's sitting on where the water droplet is sitting on those pillars, we said was 120 degrees. Great. Well, there's only two types of surface, the pockets and the pillars, and so the area fractions have to add to 1, so F2 is equal to 0.70. What about the contact angle? Well, if we have a droplet completely detached from a surface, it's not touching at all, we can see that that would have a contact angle of 180, and that would correspond to the droplet just basically being in contact with air. So the contact angle with water respect to air is 180 degrees. Great, so we have all those in. So we can say cosine of theta observed is equal to 0.3 cosine of 120 degrees plus 0.70 cosine of 180 degrees. So the cosine of the observed angle is going to be negative 0.85. And so the observed contact angle is the inverse cosine of negative 0.85 which is equal to 148 degrees. And that's almost superhydrophobic. Superhydrophobic is arbitrarily defined to be any contact angle that's 150 or greater. So this is just at that threshold for superhydrophobic. So if we drew this a little more accurately, it would look a lot more like that.